At the end of the 19th century, physicists believed the fundamental laws of nature were fully understood. Isaac Newton's classical mechanics described the motion of planets and matter, while James Clerk Maxwell's equations unified electricity and magnetism. However, when studying blackbody radiation, classical equations predicted an infinite output of high-frequency energy, a crisis known as the ultraviolet catastrophe. In 1900, German physicist Max Planck resolved the paradox with a revolutionary proposal: energy is not emitted continuously, but rather in tiny, discrete packets he called quanta, laying the groundwork for a scientific revolution. The true weirdness of the quantum world was demonstrated through the iconic double-slit experiment. When electrons or photons are fired individually through two narrow parallel slits onto a detector screen, they do not create two distinct lines as solid particles would. Instead, they build up a wave interference pattern of alternating light and dark bands, proving that every particle travels as an invisible probability wave. Most astonishingly, when physicists place detectors at the slits to observe which path the particle takes, the interference pattern disappears instantly. The mere act of measurement collapses the wave into a single physical reality. In our everyday classical world, an object has a definite position, speed, and state whether anyone is looking at it or not. In the quantum domain, however, matter does not possess determined properties prior to measurement. Instead, subatomic particles exist in a state of quantum superposition, meaning they simultaneously occupy every mathematically possible state and location at once. Governed by Erwin Schrödinger's wave equation, particles are represented not as solid points, but as dynamic clouds of probability. It is only when a physical measurement takes place that nature is forced to choose a single definite outcome. To demonstrate what he viewed as the profound absurdity of applying quantum superposition to the macroscopic world, Erwin Schrödinger proposed his famous thought experiment in 1935. A cat is placed inside a sealed steel chamber alongside a radioactive atom, a Geiger counter, a tiny hammer, and a flask of hydrocyanic acid. If the atom decays, the counter trips the hammer, smashing the vial and killing the cat. According to the standard Copenhagen interpretation, because the radioactive atom exists in a superposition of decayed and undecayed, the cat inside must be simultaneously both dead and alive until an external observer opens the box to look. Perhaps the most counterintuitive phenomenon in all of physics is quantum entanglement. When two subatomic particles interact in a specific way, their quantum states become permanently correlated. If you measure the spin or polarization of one particle on Earth, its entangled partner instantly assumes the exact opposite state, even if it is positioned light-years away on the other side of the galaxy. Albert Einstein famously rejected this conclusion, referring to it as spooky action at a distance because it seemed to defy cosmic speed limits. Yet decades of rigorous laboratory tests have proven that quantum entanglement is an undeniable feature of our universe. In classical mechanics, if an object does not have enough kinetic energy to overcome a potential barrier, it will bounce back every single time. In quantum mechanics, however, because particles behave like probability waves, a portion of the wave function extends through the barrier. Consequently, there is a real, non-zero probability that a subatomic particle will spontaneously vanish on one side of a solid barrier and reappear on the other side. This phenomenon, known as quantum tunneling, is essential to life itself. It allows hydrogen nuclei inside the Sun to overcome electrostatic repulsion, driving the nuclear fusion that provides our planet with light and warmth. To explain what happens to alternative quantum possibilities during measurement, American physicist Hugh Everett proposed the revolutionary many-worlds interpretation in 1957. Everett suggested that the wave function never truly collapses. Instead, whenever a quantum event occurs with multiple possible outcomes, the universe itself physically splits into multiple branching timelines. In this vast multiverse framework, every potential quantum outcome occurs in a separate, coexisting reality. If true, there exist infinite parallel universes containing every possible variation of history, cosmic events, and individual life choices. Today, quantum mechanics is moving beyond theoretical physics into practical technological engineering. Modern quantum computers replace classical binary bits with quantum bits, or qubits, capable of existing in superpositions of both 0 and 1 simultaneously. By entangling thousands of qubits, quantum processors can perform exponential parallel calculations, solving molecular simulations, optimizing logistics, and breaking traditional encryption algorithms in seconds. Which quantum mystery do you find most mind-bending? Share your thoughts in the comments below, and subscribe for more deep science explorations.